We've already really worked with functions. We just haven't really done like a specific, functions unit. But we're familiar with functions. I mean, the trig functions are functions. The logarithmic functions are functions. The exponential functions are functions. Like, we have been working with functions. Now we're just going to spend some time working on some function basics, some generalities, as opposed to just things that are specifically true for the trig functions. And a function is really just, think of it as a machine that takes inputs and spits out outputs. And the only thing that is absolutely a must for a function is that once you give it a particular input, there can be no ambiguity about what it will spit out as a result. We would say that for every input, there is one and only one output. Think of my favorite function analogy is the snack machine out in the hall. Right, so let's say you put in some money or whatever, and your inputs are like those codes, right? And then there's an output. So once you put in a code, we're supposed to know what will come out. So if I punch in A1 and it gives me a bag of Doritos, the next time I punch in A1, it still has to give me a bag of Doritos every single time. We can't have Doritos and Cheetos and Cheez-Its all lined up along the same column in the snack machine, because that would be chaos, and that's how fights happen. So we have to have some order to the snack machine. We say, okay, for any row, we're just going to pick one snack for that row. Now, it's okay, if Doritos are popular, it's okay to have 2 rows of Doritos. You can have 2 inputs that map to the same output. But there can be no ambiguity of mixing outputs for the same input. So the sets of inputs, like the sets of codes I could punch in, we'd say that those are the domain elements. The domain of the function is all the stuff you can plug in. For the trig functions, the domain is the set of angles, right? And the codomain, those are the set of, that's the set that gets mapped into. So the codomain for the snack machine would just be globally like all possible snacks. Now, if you go look at that snack machine, there are not all possible snacks, right? We have a limited supply, a limited selection. So we would say the range is actually the possible outputs, all the possible outputs. So even though there's many more snacks in the world, that the codomain is this global set of like seemingly infinitely many different snacks we might have, the range is just the snacks we see for that machine, is just the snacks we see that are available to us. And that's the difference between the codomain of a function and the range. So the codomain is just sort of the set of values that we're mapping into. The range is all the possible outputs that we could actually get. So a real quick, let me see what's coming. Yeah. Okay. So super quick mini example before just to talk about the difference between domain, codomain, and the range, is to think about the function. Well, let's just say y is equal to 1 over x. So x would be the input values, right? The inputs, and y's are the outputs. So we'd say that this is a function that maps real numbers to real numbers. The domain and the codomain are just the set of real numbers. Now, if you graph this function, and you can sort of see it computationally as well, but graphing it is sort of a nice visual way. If you graph it, it looks something like this. So I can have any kind of y coordinates could be reached, right? Like it keeps going down, right? So like there's no limitation there. Keeps going up toward positive infinity. There's no limitation here. So the codomain is all real numbers. But the range is slightly different. There is one number in particular that we will never get as an output, that y will never become, no matter what value for x we plug in. What's that? 0. Why not? It's okay if you don't have an explanation yet, but
because if x is a real number, then 1 over the real number is not a real number.
yeah. So, and you could almost think about what is a scenario under which a fraction could be equal to 0?
Isn't it when it's 0 over a number?
Yeah. So if we're trying to, kind of analyzing this as a function, this function is 1 over x. The numerator is fixed, right? The numerator is always 1. And if the numerator is always 1, I'm going to go out on a limb here and say 1 is never equal to 0. A fraction is only 0 when the numerator is. So I'm jumping the gun a little bit when I guess in sort of diving into this example, but I wanted us to sort of just understand there's a difference, although it might seem like a subtle difference, between a codomain and the range. And that sometimes when we're analyzing functions, we want to just sort of think generally about what does this function do? What could it possibly do? What are the types of inputs we could put in? What are the types of outputs we could put in? What is the domain of this function? What kinds of things could we plug in for x? Yep. Is there anything we can't plug in for x? 0. Yeah. So as it turns out, the domain is also all reals except 0. Right? We can't divide by 0. Right? If we plugged in 0 for x, we divide by 0. I'm jumping ahead of myself because I like getting to the fun stuff. But first, we know that we can't have different snacks mixed inside of the same row in a snack machine, right? We can't have two different outputs that yield the same, two different outputs for the same input. Now we're gonna look at some of these equations. For the most part, as fun as snack machines are, we're going to focus on functions that are defined by equations, right? So we have an equation we consider x to be the independent variable or input variable, right? Y is the output. And if I want to see if this equation defines y as a function of x, well, we need only solve this for y and then just see is that actually a function. So if we added 3x to both sides, right, we get 4y equals 3x plus 8. And then we could solve for y, and we get y is equal to 3x plus 8 over 4. And so now our question is this a function? Is there any ambiguity? If I plug in a value for x, right, if I know what my input is, then if I triple that, there's only one possible output I'm going to get when I triple it. If I add 8, then there's still only one possible output I'm going to get. Dividing by 4, and there's still only one possible output I'm going to get. This does define y as a function of x. If we look at the next example, we'll see where things can sometimes go astray. So y squared plus x squared equals 9. If I want to see if does this define y as a function of x, well, we're going to start out doing the same thing. We're going to subtract, we're going to solve for y. So let's subtract x squared. So we get y squared is equal to 9 minus x squared. And if I want to solve for y, we got to take the square root. But this is where we run into trouble. So the square root of y squared is y. But when we are the ones imposing the radical on both sides of an equation, what do we need to do? Plus or minus. And this right here is some of the trouble that we gotta be on the lookout for. Y is not a function of x. Because for any given input for x, there will actually be two possible values. And that's no good. That's like saying, I built a snack machine, but if you punch in A1, 50-50, maybe you'll get Doritos and maybe you'll get ring dings. Like, I don't know if I want to take that chance. Okay. So analytically, kind of manipulating this algebraically, this is the kind of thing that we're on the lookout for to see, are we in danger? Could we possibly get two outputs for a single input? Graphically, if we're looking at a graph of an equation, determining if the function, or not the function, determining if the equation they're showing us that they're graphing, determining if that is a function is really quite simple, because in order to be a function, we're saying that for any x, there can be only one y. And that means that if I were to pick any x value, like maybe I pick this one right here, what is this, -2 or something like that, there can be only one y. Well, there is only one y that corresponds to that on the curve. And what this means, what we're looking for is, we call it the vertical line test. So if you're looking at a graph, if every single vertical line you can draw only intersects the graph once, at most once, then it's going to be a function. What that means is no matter what x value you look at, there will only be one y value. There'll be only one spot where that vertical line intersects the graph. Over here on this side, this fails the vertical line test horribly, right? It fails the vertical line test at every point. For every value of x, there's two y coordinates. And in fact, you could even see that algebraically if you solve this for x, right? You're going to have another one of those. You'd have to take the square root on both sides, and you have a plus or minus. Here we're seeing that play out graphically. Okay. So this is a function. This is not a function. I mean, it's still an equation. I'm not like hating on it or anything. It's got some interesting behavior. Okay. Let's talk about domain and range again. We did that sort of little example in the beginning. So for starters, when we're looking for the domain of a function, we're always wondering, what is the set of values that we could plug in to this function? And the way I always try to answer it is I answer kind of from the back door. I say, is there anything I'm not allowed to plug in? What would break this function, right? So I'm on the lookout for two things. We are, by the way, restricting ourselves to working with real valued functions, which means not only are we going to say we can't divide by 0, but we're also going to say we're not going to take square roots of a negative or even roots of a negative number. There's nothing mathematically that says we can't do it. It just wouldn't be a real valued function anymore. It would be a complex valued function, right? We did some work with complex numbers already. So let's find the domain and range of this function. By the way, there's no ambiguity here, I know, because the radical was already a part of the function, right? We didn't have to take the square root on both sides. It's only when we impose the radical ourselves that we need to worry about the plus or minus business. The radical is already there, which means they mean the positive root, right? If they meant the negative root, they'd put a little negative sign in front of it. So looking at this equation, is there anything that x is not allowed to be? First, there's nothing wrong with x being equal to 4, because the square root of 0 is 0.
Can it be more than 4?
What's that?
X is more than 4.
Yeah, it can't be more than 4. So we could just observe, by the way, there's no danger of dividing by 0. So there's nothing we have to worry about there. But we do need to worry about taking the square root of a negative. So what that means is the stuff inside this radical can't be negative. So I'm going to take this expression, 4 minus x, that, I'm ignoring the radical, but whatever's inside, that has to be at least as big as 0. And then I'll just turn this around. So this means that negative x is greater than or equal to negative 4, right, if we subtract 4 from both sides. Now I want to multiply. I want to turn this into a statement about x and not a statement about negative x. So we multiply both sides by -1. Does anybody know what we have to do in an inequality when we multiply both sides by a negative? We have to flip the sign, yeah. So this means x is less than or equal to +4. So that's our domain. So the domain is, and if you look in the back of the book, you could say the domain is x less than or equal to 4, and I'd be fine with that. If you look in the back of the book, what they're going to do is probably say something like the domain is all x in the real numbers such that x is less than or equal to 4. So this is kind of the important part, like what has to be true about your inputs. They put that on the right side. What about the range? What kinds of outputs could this give? Is there anything that this function won't produce as an output? It won't produce negatives. We know that because it's the positive root, right? We said we didn't have to worry about the plus or minus because the radical was there to begin with, and if they meant the negative root, they would have put the negative root. It means the positive root. This is by design only spitting out positive numbers. So the range is a statement about x's. The domain is a statement about x's. The range is a statement about y's, the outputs. And the range is y is greater than or equal to 0. You can also tell a bit about how to find the range, I guess, and the domain for that matter. If you look at a graph of the function, so I'm putting in my y equals editor. I'll look at it in the standard window. So it looks like, and I could zoom out a bit, try to make sure I'm seeing the whole thing. It's taking its sweet time. Okay. Yep.
Maybe it's taking a break.
I think it's taking a whole break. Let's do something like that. There, I showed it. Who's boss? No, I didn't. It's still stuck. Oh, man. Okay. Well, so if you graph it, it looks like... it looks like this. And the absence of any part of the graph appearing below the x-axis, I mean, that's how we could tell the range is not, it doesn't spit out anything negative. If it did, you'd have part of the curve occupy negative y coordinates, and that doesn't happen. Also, because none of the graph occurred, to the right of this, that was sort of some confirmation that the domain is x has to be less than or equal to 4. Let's do one more. Let's find the domain and range of this function. So thinking about the two things, right, the two cardinal sins of mathematics that we're trying to avoid in these functions, what are we in danger of here?
Divided by 0.
Yeah. So what's our domain?
X must be less than 2.
Well, it can be less than 2, but it just can't be 2, so it could also be greater than 2. Right, so x equals 2 is the only thing that makes us divide by 0. What about the range? Is there anything that this fraction 3 over 2 minus x won't be equal to? 0, right? Because again, a fraction is only 0 when the numerator is, and 2 is never equal to 0. So the range is y not equal to 0. Okay, so where we had left off, we'd done a lot of thinking about domain and range and everything. So we had not yet introduced function notation, but I think we're actually kind of used to function notation in some sense. Like when we worked with, say, the sine function, right? If we say something like sine of pi over 6 equals 1/2, that's like a function notation. I'm just calling the function sine. In general, like in an abstract, we could call the function anything, and a lot of times for a general function, we'll just call it the function f or h or g. So in the same sense, in the same way that we have sine of, the way we say this is sine of pi over 6. We have that same kind of language used for any function notation. So instead of referring to things as y, we might just replace that with the function notation f of x. And it's really important to note that we read it as f of x. This is not multiplication. This is not f times x, right? It's function notation. It's a function, not a factor. So any function that we might write as a y equals, we could just write as an f of x equals, right? That's literally the only difference between the left column and the right column here. And function notation is convenient because it affords us, for example, an easy way, a more efficient way of saying find y when x equals 2, and we can just write that much more efficiently as just find f of 2, and that's what this means. So quick, like as far as like evaluating functions goes, if f of x is 5x squared minus 4, I think of the variable as just a placeholder. So if I want to evaluate f of 0 or whatever, like whatever I put here, I have to put in any other set of empty parentheses. So if I'm finding f of 0, so if I have a 0 here, then a 0 has to go here. And we just get 0 minus 4 or negative 4. F of 0 is negative 4. F of negative 3, we're going to do the same thing. So 5 times something squared minus 4. Whatever number goes inside the parentheses here has to go inside of any set of empty parentheses on the other side of the equation. So we have 5 times 9 minus 4, which is 45 minus 4, or 41. So there's f of negative 3. Here we're using f, but we could use whatever letter you feel like using. G of x, h of x. Greek letters are popular. Everybody likes Greek letters, I guess. All right, so here we have a couple of functions. We want to find f of 6. So first of all, I've got an f function and a g function. So f of 6 means I'm going to make sure I use the f function and then replace x with 6. So this is what? 12 over 6 minus 2, or 12 over 4, which is 3. G of negative 2. So I'm going to plug in negative 2, but I got to make sure I'm using the g function. So we have the square root of negative 2 minus 1. And we get the square root of negative 3. Something weird happens here, though. If I were, on Monday, when we were talking about questions like this, right, functions like this, we were defining and mostly talking about domain and range. Things we're allowed to plug in and things we're not allowed to plug in, and we noticed that, or I stated, our focus is on real valued functions, which means the domain of this function would not include anything that makes us take the square root of a negative. So we plugged in negative 2. That does, in fact, make us take the square root of a negative. So what we would say is negative 2 is not in the domain of g of x, and as a result, g of negative 2 does not exist. If we expanded and defined this from a function of from real numbers to complex numbers, if we wanted to allow for complex valued functions, well, then we could find it and we'd simplify it. We'd get root 3 times j or something. F of 6 times g of 2, well, we already found f of 6. We did that in part A. So this is going to be 3 times, and we need to find g of 2. Oops. So g of positive 2, this is the square root of 2 minus 1, or square root of 1, which is 1. So that means f of 6 times g of 2 is 3 times 1, or just 3. So far, so good. Okay. So mostly, with function notation and evaluating, we're just saying, replace x with this value. You can also plug in expressions to the value, like find the function that results if we replace our input x with, for example, 3c squared. So the f of x function, as defined in this problem, is x squared minus 4x, which means whatever the input is, we're first going to square it and then subtract 4 times that input. You got enough water, Sydney? Yeah, good. Sorry, I was about to say I'm not trying to pick on you. I guess I was trying to just pick on you a little bit. Like, I'm not trying to make you feel bad. I just thought that was entertaining. Okay.
It's funny, so.
Big water jug. So 3c squared is our input in this function, so that means we're going to replace, or our input in these empty sets of parentheses, 3c squared. And now we just do algebra, which is our favorite. What is the square of 3c squared?
9c to the 4th.
Uh-huh. And 3 times 4 times 3c squared?
Minus 12c squared.
Yes. That's, we could factor it if we felt like it, but I mean, this is the function, this is equal to f of 3c squared. If we want to evaluate f of a plus 5, it works the same way. I mean, my f function, right, again, I just think of my inputs as a set of empty parentheses. So I have like placeholders, right, for my input. This time we're going to plug in a plus 5 and a plus 5. And again, we get to do algebra, which is our favorite. What's a plus 5 squared?
A squared plus 10a plus 25.
Yes. We are all getting very good at resisting the temptation to distribute over addition, distribute exponents over addition. And then we just distribute this negative 4. So we have minus 4a minus 20. And now the only thing left to do is combine like terms. So we get a squared plus 6a plus 5. And, I think that will factor, so we could factor it if we like. It would be something like a plus 5, a plus 1. Right? Yeah.
Do we need to factor?
What's that?
Do we need to factor?
Not unless you're instructed to do so. I mean, sometimes there's reasons why we might want to factor. Like for example, if I encountered a problem that says, here's this function f of x as they gave us, and they said, tell me where f of a plus 5 is equal to 0. well, then it's really in our best interest to factor because it's easy to tell where this is equal as well. Other questions? Okay. So we can compose two functions if the domains and codomains line up nicely, by which I mean, and for us, for the most part, they will, because we're really just looking at functions that map from reals to reals. And so let's say we have our a function, maybe you have a domain A, a codomain B, and we have some other set here, C. And if, let's see, in this definition, G maps from A to B. So there's my G function. Right, so for some element A here, if I send it through the G function, it sends me here. There's G of A, which is in the B set. Right? Is that okay? This is essentially what functions do, right? You take stuff in one set, sends you over into another set. In this definition, it also says that F maps from B to C. So, like, if I took some element B in the B set, I could send that through the F function and get, F of B. That'd be some element in C. But if you'll notice, since G maps from A into B, G of A is itself an element of B. So I could, if I wanted to, take this guy and map it into C, right? Any element that's in B I can send through the F function. And this would give me F of G of A, right? Whatever that value was. What this definition says is that if I have a couple of functions like this, where like my G function goes from A to B, and my F function, I have another function that sort of picks up where the G function leaves off, right? Like so it's almost like a leapfrog kind of a thing. I can get from A to B using the G function, and if I can get from B to C using the F function, well, this affords me a way using G and F together. We call it a composition that says, you know what, if I can do this, why can't I just find a function that will take me straight from A to this element over here? And that's what the composition does. That's what it says in this definition. So it says if G goes from A to B and F goes from B to C, the composition is a function from A into C defined by this way. In particular, we use this little circle to mean like composition. That's like F composed with G. But I always, if I'm finding a composition, rewrite it in this way. F circle G of A is the same as F of G of A. And this is sort of the useful kind of computational way to think of a composition of functions. So for example, if I have a couple of functions, both of these, by the way, map from reals to reals. That means that the composition is defined, right? Where the G function spits out is precisely where the F function maps from, right? So certainly if your sets are all the same, then your compositions are defined. We have our F function is 1 minus 2x, and the G function is 3x squared minus 5. So if we want the function F circle G, or F composed with G, F of G of x, the first thing I do is just rewrite it as F of G of x. This says that I'm just going to take the G of x function and plug that into F. So G of x is 3x squared minus 5. So this is F of 3x squared minus 5. So we are now at a position where we just want to plug in this expression to the F function. It's like the ones we did on the previous page. So our F function, 1 minus 2x, this is 1 minus 2 times whatever the input is, but this time my input is 3x squared minus 5. And now we get to do algebra. Try to do it correctly. If we distribute the 6, or the 2, we get 6x squared plus 10. So we get 11 minus 6x squared. There's our f of g of x function. Here's what this says is if I wanted to find, f and g both map from reals to reals. So if I wanted to find, say, f of g of, I don't know, 3, okay? Normally we'd say, okay, well, I have to figure out what g of 3 is, right? So g of 3 is 3x squared minus 5. So 3 times 3 squared minus 5. That is 9 times 3 is 27. 27 minus 5 is 22. So there's g of 3. And then plug this into the f function. So f of g of 3, this is f of 22, which is 1 minus 2 times 22. And this is 1 minus 44, or negative 43. When we find a composition, though, when we find the composition function f of g, if I want to find f of g of 3, I could equivalently just take my input 3 and plug it in for x in this expression. It'll be the same thing as if I found 11 minus 6 times 3 squared. 11 minus 3 squared is 9. 9 times 6 is 54. And this is negative 43. We get the same thing. That's not a coincidence. That is by design. So in part B, let's find the composition going the other way. Let's find g of f. Again, both functions map from the real numbers to the real numbers, which means the composition is defined in both directions, right? The f function leaves off where the g function picks up. So we want g of f of x, which is g of f of x. The f of x function is 1 minus 2x. So we want g of 1 minus 2x. And this is the expression that we're going to plug into the g function. And the g function is 3 times something squared minus 5. And so this input will be 1 minus 2x. Now we get to do algebra. If we square out the 1 minus 2x, we get 1 minus 4x plus 4x squared. And we subtract 5. We got to distribute this 3. And then we can combine like terms, so we get 12x squared minus 12x minus 2. So this is g of f of x. And I think probably the most important thing we might observe from this is that in parts A and B, we got different answers. Right, different functions resulted. And so function composition is not commutative. How's that so far? Okay. All right. So the next thing we're going to do is stuff that we've really kind of done in other, in other contexts. We've done this. We did it in the pre-calc 1 when we were we spent a day once plotting out like exponential functions. We did this a couple chapters ago when we were like plotting out the like sine and cosine, like Andrew's favorite chapter. So we're going to do the same thing just for like an arbitrary kind of algebraic function. A graph of a function is nothing more than, it is a visual representation of all the xy pairs that make the equation true. So if we're graphing the function y equals 9 minus x squared, one of the easiest ways to do that is simply to, or one of the, I will say, simplest ways conceptually, is just to plot some points. Take a, first thing I'm going to do is observe what's the domain of this function. And that's another way of asking, is there anything we can't plug into this function?
I don't think so.
Yeah, we can square anything, right? We're not in danger of dividing by 0 because there's no x's that appear in the denominator of a function. There's no radicals, so we're not in danger of taking like a square root of a negative, which means we can plug in any real number we want. So the domain is all real numbers, and I'm making a point to say that because when I'm plugging in some values, I want to make sure maybe I pick some positive values, some negative values, like maybe a kind of I want enough to be able to observe the pattern, like a visual pattern here. So maybe I'll do something like and this might even be more points than I need, but I'm just taking a collection of numbers. And then in the other column, we're going to find the y-coordinates, 9 minus x squared. And if let's see, 9 minus negative 4 squared, 4 squared, 16, what's 9 minus 16? Negative 7. 9 minus negative 3 squared is 0. 9 minus negative 2 squared is 5. This gives us 8. And at 0, we're at 9. What happens when I plug in the 1, 2, 3, and 4, the positive values? Yeah. So what are the values? Like if you look, can we make a prediction about what all these values will be? Mm-hmm. Right, and we can tell by plugging it in, right? You could check, but the only time x appears in the formula for the function is when we have an x squared. X squared is the same whether it's positive or negative, right? When you square it, it's going to be positive. So the fact that the only time x appears is as the x squared term means there's going to be some symmetry in the outputs. And then, this gives us a set of values, a set of points. So in the top row we have negative 4, negative 7, negative 3, 0 is a point, negative 2, 5, negative 1, 8, 0, 9, 1, 8, 2, 5, 3, 0, 4, negative 7. So we plot some points. At 4 and negative 4, we are at negative 7. At negative 3 and 3, we're at 0. At negative 2 and 2, we're at 5, so that would be up here. Oops. at 1, and -1, we're at 8, and then 0. So it looks something like this. Probably not a huge shocker to folks that we get something that looks like this. If you graphed any quadratic equations, you know they have this kind of basic shape to them. One thing we want to do for plotting, you know, for sketching out a graph, we don't want to say, okay, we're done, because that actually, if we stopped here, we'd be implying that the graph just stops. So we wanted to make sure we plotted enough points to observe the pattern, to see what this behavior is like, and then just indicate that this thing continues. You know, as x gets huge in either direction, it's just going to get, you know, grow further and further negative. So we want to make sure we indicate that.